So we are in Augustus 5 and 6, and this is the malware track. Couple key things. Please make sure you have your cell phones off or on vibrate. Also at the end, make sure you take some time to do the speaker feedback forms. It helps them learn, helps us figure out what things to do better here. So I won't say much more so we can get started since we're a little late. Here's Lucas.
All right. Hey guys, my name's Lucas, or Snare. I'm from Melbourne, Australia. I am the principal consultant at a company called Assurance in Australia. We're a pen testing outfit in Melbourne. And yeah, it took me a while to get here. I'm going to talk to you guys today about EFI-based malware. So infecting current Apple hardware at the firmware level. So I'm going to go through a few things here to begin with. Sort of what my goals were when I set out doing this research, and a bit of background, some prior work that's been done in the area, all that sort of stuff. A bit of info on EFI sort of fundamentals, how it all fits together, and what components there are that we can mess with. Then doing some bad stuff with EFI, how to, what kind of things we can actually do from within EFI and attacking the kernel and all that sort of stuff. A few things about persistence, how we actually persist a rootkit in EFI on a Mac. Then a few evil MAID attack scenarios that we can carry out with EFI, and then a few defensive measures that we can use to mitigate this type of attack. So the reason that we're really all here is because I wanted a cool boot screen on my Mac, right? So I wanted to play with like EFI graphic stuff in the pre-boot environment, and as soon as I started playing with that stuff, I realized pretty quickly that it's probably a really good place to attack the system from, right? And of course all that stuff's been done before, but it kind of only occurred to me at that point that firmware, you can do a lot from the firmware, right? So I didn't really have a lot of background in firmware or kernel stuff, bootloader stuff or whatever, so dug in. So there's been quite a few different bits of research done in this kind of area before, like going right back to MBR viruses and that kind of thing that infects boot code and the MBR on the disk, and right up to more recently, John Heisman at NGS spoke at Black Hat a few years ago, talking about the potential for EFI stuff. And to be honest, I'm quite surprised that we haven't seen stuff in the wild, since his talk, because he covered a lot of great stuff. Core Security dudes and Invisible Things Lab have done a lot of good work with attacking BIOS and UEFI as well in the last couple of years. Definitely worth checking out the stuff that they've put out. Androzine speaking this afternoon, talking about rootkitting BIOSes, which is going to be pretty badass, and it's going to scare the shit out of everyone, basically. There's been heaps of stuff done. It's all really cool. So the main goal I set out to achieve, I guess, was to be able to backdoor a machine, preferably without any evidence on disk, because we're in the firmware, so we've got a few more options as far as storage goes. Preferably be able to persist forever without, relying on stuff being written to disk. So if the machine gets wiped, it's still infected, the disk gets replaced, it's still infected, right? We want to be able to patch the kernel at boot time and do a few other things before the kernel is actually executed. And to work regardless of whole disk encryption, because if you don't have whole disk encryption on your laptop these days, you're crazy. So I think everyone who matters probably has whole disk encryption on their laptop, so that's going to be a part of the whole scenario, I guess. So all that stuff together, sounds pretty hard. EFI makes it a lot easier to build this kind of thing, which is pretty cool. So some fundamentals about how EFI works. It was originally developed at Intel as a replacement for the legacy PC BIOS to address some of the limitations that Intel saw in the PC BIOS, and to become the pre-boot environment for all of their upcoming IA64 and whatever else architecture gear. Whether or not it addresses all of those limitations is open for discussion. It was originally called the Intel Boot Initiative, and it was handed over to a community group a few years back in 2005 or something, I think, which is when it became UEFI. So it was handed over to the Unified EFI Consortium and developed as an open source project for the actual implementation, and the specifications developed by the UEFI Consortium. Because UEFI is not a product, it's a specification, right? So it's a specification that defines a firmware interface, and Intel has also implemented that. So EFI is pretty modular, which makes it great to develop components for, like compared to developing for traditional BIOS, where you have to write shitty like 16-bit real mode assembly and stuff, which kind of sucks. So it comprises a bunch of core components, which are sort of the key like main phases of EFI's startup, which I'll talk about a little bit more in a sec. Some applications, like there's a telnet client, FTP client, all that kind of stuff, and there's a shell, like for a command shell kind of access that you can boot into with refit or whatever. Drivers to support hardware in the pre-boot environment, and then bootloaders for obviously loading operating systems. So the core components of EFI reside on, as you would expect, the firmware flash on the logic board or the motherboard. So the Mac's called logic board. Along with a set of drivers for managing the sort of core set of hardware that's on the logic board and built into the machine, enough to boot the system up, and then the kernel can take over and control whatever hardware it needs to. So applications and third-party drivers for other hardware can reside either on disk or in the firmware data flash along with the full EFI firmware, or on option ROMs for PCI devices, which is pretty cool. So a little bit about EFI terminology, in case I refer to some of this stuff. So this is like a system table, which is just a table of data structures and function pointers for that applications and drivers that run within the EFI pre-boot environment can access. So that system table contains like pointers to all of the other tables, and that's what gets passed to a driver or an application when it first gets executed. So it has access to all this stuff within the EFI pre-boot environment. The boot services table contains a pile of functions for memory allocation and managing protocols and loading images and stuff. So things that you need to access from your device driver or application while EFI is present before the operating system runs. So then the runtime services table contains a set of functions and data structures that are accessible in the pre-boot environment, and then also once the operating system is present, it can actually call back into EFI to do various things like timing stuff, virtual memory, converting addressing for when the bootloader hands over execution to the kernel, builds a memory map and has to convert all the addresses from the physical addressing that's used in EFI's environment over to the 64-bit addressing that's used by the kernel. Other stuff like resetting the system, so there's a reset function to warm reboot. Capsule management, which is used for handing EFI executables back to the pre-boot environment from the operating system, which is something that Apple uses as to write firmware updates to the machine. I'll talk a little bit more about that a bit later. And also variable services. So when you run the NVRAM command on a Mac, you're inspecting obviously the NVRAM, which is accessed from the OS via IO-kit, but in the EFI environment you can access the same data store through the EFI variables functions. So that's where the boot device, like the PCI device path to the boot device, is stored. The configuration table is for custom runtime services. It's not particularly useful for us. Actually, it could be. Anyway. So, developing for EFI, Intel provides the EDK, the EFI development kit. Well, now it's provided by the community group, but so that includes Tiano, which is Intel's reference implementation of the EFI specification, and this is what most like IBVs use as their basis for implementing a new BIOS, a new UEFI BIOS or an EFI BIOS, and this is pretty much what Apple uses as well. It's written in C, which is great because I hate writing 16-bit real mode assembly and I don't really know a lot about it. But I'm pretty good at C, so that is really helpful for me. It's nice and high level. Everything's laid out nicely for you. EFI also sort of reuses a few like older technologies that are used elsewhere. Like it uses a FAT file system for the EFI system partition. The command shell looks like DOS, which is hilarious. And it uses PE32, like a subset of the PE32 executable format, which is great because IDA Pro understands it. And so if you've got x86 or whatever EFI drivers that are using PE, you can just dump them into IDA Pro and disassemble them. It's pretty gigantic as well, which is kind of scary when you look at the work that dudes like the Invisible Things Lab people have done with finding bugs in like the PNG renderer that renders the boot screen and stuff like that. Like there's a huge amount of code and a huge amount of, you know, untested and unreviewed code probably that, you know, can contain bugs, and they've already demonstrated that there are quite a few, and I don't think anyone's looking particularly hard, so there's bound to be a lot more. I could be wrong. People could be looking for them, and maybe they're out there. Who knows? So it's it's a pretty giant code base. It's you know, using that not particularly scientific method of counting lines of code. So there's about twice as, you know, many lines of code as are in the macOS kernel. The spec itself is 2,200 pages long, which is pretty huge. And looking at some of the core like protocols that are defined by the spec, like it looks like an operating system, right? It's got, you know, network stuff, it's got crypto stuff, it's got like, you know, a UI forms library for, you know, for generating UI, you know, graphical UIs in the pre-boot environment. And people have written, you know, web browsers for it and stuff. So it's pretty huge. So the EFI boot process. I mentioned before there are a few phases of the core sort of EFI boot process. When the system's first powered on, the sec phase takes control, and it serves as like a root of trust for the system and does some like very basic initialization of the system. After which it hands over to the PEI phase, which is the pre-EFI initialization. PEI basically like initializes the CPU and other chipsets on the board that are essential for, you know, the operation of the machine, other board stuff. And then it hands over to the driver execution environment, DXE phase. DXE is pretty much where all the where the bulk of the initialization of the system takes place. So this is where drivers are loaded from the firmware volume, where PCI buses are initialized and enumerated, and all the devices on the bus are polled for option ROMs on the, you know, if they have expansion ROMs, they'll be ready and mapped into memory, and drivers loaded from them. So after this, you know, the system's all set up and all the drivers are in place for EFI to access all the hardware, it hands over to the BDS phase, which is the boot device selection phase. So BDS, so when you hold down the option key on a Mac and you get your cute little boot menu thing to choose from the available disks to boot from, that's the BDS phase. So the BDS phase looks at the NVRAM to find the boot device that's been set. So the PCI device path is stored in NVRAM to the boot device, and then it looks at the boot device and finds the bootloader, you know, according to the volume header or according to other NVRAM variables depending on how it's configured, and then loads the bootloader and executes it, which loads the kernel and executes the kernel. Typical. So that's kind of how the EFI boot process works a little bit, which I'll talk about in a slightly different way in a sec. So onto the fun stuff, actually doing some bad things with EFI. So the modularity in the SDK, as I've kind of already indicated, makes it pretty nice to actually develop in compared to developing for BIOS hacks. So I guess there's a few things that we can do. We build a rogue driver. We could also Trojan the bootloader or whatever else. But I think that the easiest way is basically just to build a malicious driver that gets loaded early on somehow, whether it be out of an option ROM or by a shim bootloader or something like that. Register some callbacks for events within EFI, hook some boot services and runtime services, and functions within protocol blocks and all that sort of stuff, typical function hooking stuff, and mess with things, I guess. So being a pretty generic firmware interface, it's pretty easy to write something that's going to be supported on across a whole range of EFI-based systems. So there's also the EBC EFI bytecode format, which is a bytecode format specified by the EFI specification, with which you can compile drivers into EBC that will work on IA64 and x86 and whatever else. There are only a few platforms I suppose there's ARM as well for EFI. So you can build cross-platform malware with it. It's pretty cool. So the first thing to talk about with actually attacking things from EFI is attacking whole disk encryption, because that's kind of cool. So if you don't have file vault enabled, that's kind of what the layout of the hard disk probably looks like. Probably less shiny than that, but you've got the EFI system partition on the at the start of the partition table, which, as I said, is not really used by Apple's implementation apart from staging firmware updates. Then you've got your OS partition, which contains the operating system and all your stuff, and the bootloader. So the bootloader is stored on the OS partition in this case. Then at the end of the partition table, there's on a macOS 10.7 machine, there's a recovery partition. So when you hold down the Command R and you boot up into recovery mode, you can reinstall your machine or whatever. So when you enable File Vault, the OS partition is encrypted. So you have to be able to load the bootloader somehow. So basically they just cram the bootloader onto the recovery partition, which already has a bootloader, I guess, for its own purposes. So we can't actually access the bootloader until the OS partition is decrypted or unlocked. I think is the core storage terminology for that. Yeah, so it's still on the recovery partition in plain text, or clear text, unencrypted, free for us to mess with. So the boot process with File Vault enabled is platform firmware initializers, loads the bootloader from the recovery partition. The bootloader prompts the user for the passphrase, so that's the passphrase entry prompt for File Vault is actually presented by boot.efi, and then uses that passphrase to unlock the core storage volume that the OS is on, and then executes the kernel. So I guess the first thing to look at with regards to attacking File Vault is a keystroke logger within EFI to steal the user's passphrase. So this turned out to be pretty simple to implement. So there's a protocol that's defined by the EFI specification called the Simple Text Input Protocol, which is used for console input, right? There's the Simple Text Output Protocol for console output. So the Simple Text Input Protocol is has a protocol block like structure that contains pointers to all the functions and data and stuff for the protocol, including the read keystroke function, which reads a keystroke. So when you press a key, that gets called. So basically, we just want to hook that function and keep a buffer of all the keys. Pretty traditional keylogger kind of thing. The one problem with that is that when we get loaded during the DXE phase, the instance of the Simple Text Input Protocol that's installed on the console handle at that point is not the same one that's used to receive keystrokes for the passphrase entry screen. So what we need to do is use the register for protocol installation events within EFI. So there's a whole series of events you can register for, which is awesome. So we just register for and wait around until until another instance of the Simple Text Input Protocol is installed on that handle, and that's when the bootloader installs one to read keystrokes for the passphrase entry screen. So yeah, we can hook that, and that works pretty well. We can save that in a buffer, stick it in an NVRAM, wait till the system's booted, and send it off over the network or whatever. Another way I guess we could do that, some guys recently have done a lot of work reverse engineering File Vault at the sort of core storage like volume level. I don't know a whole lot about that, but I think like using their research, it probably would be pretty reasonable to be able to actually steal the AES key out of memory as well once the disk is decrypted. But I think once you got the passphrase, it probably doesn't matter too much. But I think it's definitely worth looking into as well. And yeah, Apple provides some handy dandy debug logging there in their boot.efi binary, which is kind of cool. So the real fun stuff, I guess, comes with attacking the kernel, right? That's generally what we're going to be aiming for. I'll try to get all my jokes into one slide there. So I guess we want to patch the kernel from EFI, right? So we want to get some malicious code in there and have some fun with it. So we need to find a place to put some code. We hook some kernel functionality to point it at that code, and we probably get execution during the kernel initialization to actually install rootkit hooks, tentacles throughout the system, and all is good. The problem with that is that the kernel isn't loaded when our driver gets loaded or our application gets executed within the EFI environment. So that's why I'm using a driver for this, because we have the opportunity to wait around and stay in memory until right at the very end of EFI's initialization, and even past that if we allocate runtime services memory, which I'll mention a bit more about in a sec. So this is where the exit boot services callback comes in. So if we have a look at another view of the EFI boot process with a slightly fancier diagram, we've got the core phases of EFI that I mentioned before, sec, PEI, and DXE. So they run through their stuff, and then drivers are loaded by DXE, including our bad driver. Hands off to BDS. Loads a bootloader, blah blah blah. So bootloader loads the kernel, following which it sort of prepares the environment for kernel execution. Part of which is telling all the drivers in the system that if they need to clean stuff up, that they should do it now. So exit boot services, anything that registers for an exit boot services notification will get called back into and get the opportunity to execute code again before the kernel gets executed. So this is a really good place for us to mess with the kernel, because at this point the kernel is loaded into memory. So in order to actually mess with the kernel, we need to find it. So the start of the kernel image is at that address. If we have a look at the OTOOL, the Marco binary with OTOOL or MarcoView or whatever, we can see that the first segment is loaded at that address. If we have a look on a live system in a debugger, we can see the Marco magic number for the 64-bit Marco binary there. So that's where it is. So in the EFI environment, as I mentioned before, it uses a flat 32-bit memory model without paging, rather than the canonical upper and lower halves, model that a 64-bit model that the XNU kernel uses. So so in 32-bit mode, we basically just truncate it, and it's at that address there. So what we're going to do is we're going to inject a payload somewhere. I'm going to patch a kernel function, point it to the payload. Because we don't have a lot of room to put our payload in, so what I've done in my proof of concept is use the trampoline payload that bounces off to a second stage payload and finds a second stage payload in. I've used an EFI variable, but you could also use runtime services memory that's allocated within EFI and call back into from the kernel over the network, whatever else. So I've used the Silvio Cesare page alignment padding thing that's been around forever, which is awesome. Still works. End of the text segment. So segments are page aligned. There's a bit of padding at the end because segments don't take up the entire page usually. So on a default 10.7.3 kernel, we've got about 4K, almost an entire 4K page of data to play with. It turns out on 10.7.4, which I have on this machine, we only have about 506 bytes or something, which is still not too bad because it's plenty of room to stick a small trampoline payload. So that's pretty sweet. Alright, so we've been called by exit boot services, and we know where we can store our payload, and how much space we have to store it. So what are we actually going to put there, and how do we get it called? So I'm going to answer the second question first, because it makes more sense that way, funnily enough. So we patch a function in the kernel's boot process. I've chosen to use load init program because at that point most of the subsystems are initialized and we're ready to actually execute the init process. So everything's pretty well sorted out as far as kernel land goes. We basically just patch a function with typical inline hooking technique, and we overwrite the first 8 bytes or whatever of the function with a relative jump to our payload, which is stored in the padding. And then the trampoline payload. Basically just, because we've inline hooked it, it needs to save the CPU state, locate the next stage payload somehow, whether that's EFI variable, in this case it is, or whatever else, initialize the payload, it has some initialization routine to install rootkit hooks into the kernel or whatever, restore the patched instruction at the start of the load init program function that we've used to jump there, restore the CPU state, and jump back to load init program, which has been fixed up so we can let the kernel continue booting and not crash horribly. Yeah, so that's pretty much what I just said. Yeah, same thing. So a little screenshot of the code for preparing the trampoline function, trampoline payload, sorry. So what we need to do first is find the load init program function in the kernel image. So we have to parse the link edit segment, which contains the symbol table, and find the load init program function in memory, and then save the first 8 bytes of that function so that we can restore it later. Calculate a displacement to where our payload's going to be stored in the page alignment padding, and then store the. We also need to so calculate a displacement to the page to the payload, and then overwrite the first sort of set of instructions in the load init program function with our E8 relative jump to our payload. And we just copy that into the page element padding. So sweet. So once we're actually in the kernel, what do? I won't go into a whole lot of detail about this stuff because it's kind of been covered pretty well over the years as far as macOS kernel rootkit stuff, like Dino Jobsivs and a whole lot of cool stuff. And yeah, there's lots of stuff around. Check out Fractal's blog because he's done lots of cool shit in that area. So we can hook syscalls, we can install network kernel extension callbacks to get execution when, you know, packets come in, go out, sockets are open, sort of stuff. We install trusted BSD policy handlers, which is a kind of a neat way to get execution in the kernel. We can patch all the things in the kernel, whatever we want to do. There's plenty of stuff. The example I've used is a pretty cheesy sysint hook. So that's what my demonstration later will use. So basically just overwrite the entry in the sysint table for the kill syscall, and you know when kill gets called, my function gets called instead, and then it checks for the magic number and carries on. So onto persistence. So there's a few options as far as persisting an EFI-based rootkit on Mac. So in ascending order of awesome, we can mess with the bootloader, which I'll explain why I think that's at the start of the list there. We can put stuff on the EFI system partition, which is not particularly useful in this case. Actually, it's not in ascending order of awesome. I put them out of order because I'm an idiot. Okay. And following that, we've got PCI device expansion ROMs, which is pretty sweet, and then firmware flash, which is the ultimate goal, really. So messing with the bootloader. Since we're already on disk, we might as well just patch the kernel or install a kernel extension rootkit. I guess there's a few reasons for not doing that, because it is kind of useful for evil MAID attacks where the OS partition is encrypted and we've only got access to the recovery partition. So we shim, install a shim bootloader that loads the driver and then loads the real bootloader and carries on, or something like that. So it's even with firewall enabled, we can use that in an attack. So it's all right. It's a decent option, but we're on disk, so that's whatever. The EFI system partition is actually not such a great option. This probably should have been first since it's 1 out of 10. As far as I can tell, it's not really used apart from staging firmware updates. I don't seem to be able to get any EFI drivers to be loaded by EFI off this without using my own bootloader. If anyone knows how to do that, it'd be awesome. So yeah, that kind of sucks. So expansion ROMs are awesome because so basically what happens is PCI gets initialized, devices are probed for option ROMs. If they have an option ROM, their option ROM gets mapped into memory and it gets parsed for any drivers. You can store an EFI driver and a BIOS driver with an option ROM, which is also kind of neat. So you can have something that can attack legacy BIOS and EFI, which pretty cool. Then if you use EBC, if you're EFI drive, you can own everything. So DXE phase loads any drivers that have been found in expansion ROMs. So this is used for things like Pixie, also like graphics hardware for so that the graphics card can provide a driver to the BIOS or UEFI in order to for it to communicate with the graphics card in the pre-boot environment and actually have graphical console. Another one that is pretty common is like SATA adapters might have an option ROM to provide a driver so that disks connected to the SATA adapter can be communicated with from EFI or from BIOS, so you can boot off them. So it's kind of hardware specific because we're dependent on having a device there that has an EFI, has an option ROM on it. But fortunately, a lot of stuff does these days. Like all the graphics hardware in the iMacs and Mac Pros have option ROMs on board, and I believe the Intel HD graphics 4000 whatever chipset that's used in the current MacBook Pros for the integrated and for all the MacBook Airs actually does have an option ROM as well. I haven't really played around with it too much, but it's a pretty good place to store our wares. VMware's Ethernet interfaces do, which is hilarious, but it's really useful for testing this kind of stuff. And we can actually write to expansion ROMs from the operating system, quite often using flash ROM or other techniques to talk to them, reversing the graphics firmware update mechanism is a good one. So that's pretty cool, because we're not storing anything on the disk. We get execution, before the bootloader is loaded and all that sort of stuff. And you can pull the disk out, erase it, whatever. It's machine's still owned, which is pretty cool. So firmware flash, where the actual UEFI core stuff is stored, is I guess the ultimate goal. But Apple actually don't make this easy for you. So it's hardware specific to a certain extent, but not quite so much as the option ROMs, because everything has to have a firmware flash, right? It just depends on the chipset that we need to talk to, or in order to talk to the EEPROM via SPI to flash it, right? So if we can successfully do this, then we can, Trojan the SecPhase, PEI, DXE, like all the core EFI stuff. We can, stick our own custom drivers in, whatever we want. Again, this can be written to from the operating system using flash ROM. In a lot of cases, where the chipsets are supported, quite a few of them are on Macs, I've found. So if that works, that's pretty sweet. So just a little bit about how the firmware update process works. So basically, Apple copies firmware update volumes to the ESP, to the EFI system partition, and then they're written to the flash on a reboot. So older machines use a firmware volume that contains the entire new firmware image to write down, and just reblesses the disk with basically what is a shim bootloader, I guess, which is the EFI updater app, which then writes a new flash out when the machine's rebooted, and then it sets the old bootloader back and reboots again. Newer machines use EFI capsules, which is a way of communicating with EFI and passing executable code back to EFI from the operating system. So you map, your stuff into memory at a specific address with a specific mailbox format, and EFI looks for that when it starts up and grabs the drivers in that and whatever else and dispatches it and writes it out to the firmware. So manipulating this firmware, all of the format of the capsules and firmware volumes and stuff is all specified as part of EFI, so there's some nice documentation on how to do it, which is pretty good. So a capsule basically just has a firmware volume inside it. A firmware volume has a set of files. It's just a file system, like a flash file system. There's a bunch of tools around already for manipulating like Phoenix and AMI UEFI-based BIOSes, but they're mostly aimed at doing slick mods and pirating Windows and whatever else, like messing with ACPI tables and stuff for Hackintoshes. So they're not actually very good for replacing drivers in BIOS images. So I had to write my own for that. And another guy very recently has released a tool for doing this as well, which is very cool and worth having a look at. So there's the output of my tool, which basically just passes the firmware volume and spits out all the drivers. So it disassembles the firmware volume and pulls out all the drivers and recursively, so that we can disassemble them and then reassemble a new firmware volume with our own drivers in it, as well as all Apple stuff. So you can see like the PEI modules there and the DXE core, sections of the BIOS and some drivers. So yeah, we basically just want to replace or add a driver in the volume and then write that back to the firmware, write that back to the flash, sorry, with flash ROM or however else we want to do it. So there's a few problems with that. Like someone who used to work at Apple told me that that Apple's boot ROM checks the signature on the firmware, which stands up to my experimentation, because I bricked a machine writing a Trojan firmware back to its firmware flash. So and there is a signature block at the very end of the firmware volume. So I guess that's the way it is. I guess there could be some other ways to get around that. I haven't really looked further into that, but like as I said before, there have been quite a few bugs discovered already, and being able to get execution otherwise. So newer Macs actually use a write protect flag pin properly on the flash. Some of the old machines, like my MacBook, do not, so you can actually write to it with flash ROM from the OS. So if they do use the write protect flag, we need to actually write to it from EFI, because that's where it's done by legitimate firmware updates. So again, see the Invisible Things talk. So that's what happens when you do brick a machine. And I had to pull the logic board out, and somehow luck was with me, and I managed to write the firmware volume that I pulled off back onto the thing using a bus pirate. And that machine boots again now, which is kind of surprising. Okay, so onto evil MAID attacks. So there's a few attack scenarios with evil MAID type attacks that we can do with EFI. I guess the most simple one is we can just change the boot target and boot off something else with a malicious bootloader that does some stuff and then continues on. Maybe writes a shim bootloader out to the disk, or flashes an option ROM, sticking a payload into the option ROM or whatever other stuff that I've kind of talked about before. I guess we can also remove the disk and write stuff directly to the disk and do any of those things. That's, I guess, getting harder with Apple Gear because they're making it a bit more difficult for you to actually get at some of this stuff. You can still remove the SSD, I guess, but it's starting to become a bit of a pain. So there's a new, I guess, attack vector for evil MAID attacks, which is Thunderbolt. So this presents some interesting options for us. So Thunderbolt is a combination of PCIe and DisplayPort over one cable. So there's a Thunderbolt controller chip, on the logic board, and then there's a Thunderbolt controller chip in the device, and then everything in between is Thunderbolt, and out the other ends is DisplayPort and PCIe. So Thunderbolt does PCIe. PCIe devices, as we know, have option ROMs, so we can stick malicious stuff in option ROMs on PCIe devices, on Thunderbolt devices. So my first incarnation of this attack was using a SATA. I developed for Express Card. So I had a SATA Express Card adapter, SATA Express Card adapter, which has an option ROM on board, which I wrote a malicious driver to, and then connected it to my old MacBook Pro via the Express Card slot, and to my new MacBook Pro, my MacBook Air via the Thunderbolt port with a Thunderbolt to Express Card adapter, and that just electrically goes right through, so it's works pretty well. But I thought that was pretty sweet because it's a pretty small, portable little apparatus for attacking, for carrying out an evil MAID attack, right? But it gets better. So Apple releases their new machines, and they've got these little Thunderbolt to Ethernet adapters. So these guys have a Broadcom BCM 577 something chipset on board, which has an expansion ROM on board to store the Pixie firmware, and also settings and stuff for the Ethernet chipset, right? So pretty typical Ethernet chipset, but I was stoked that it actually has an option ROM on there. So the process for carrying out this kind of attack, I guess, would be something like this. We attach the adapter, we power on the system. The driver is loaded from the option ROM on the adapter, and then the driver deploys its payload, whether that's flashing another option ROM on something on board, writing to the firmware flash, writing to the disk, whatever, a few options. And all that happens before the file vault, like passphrase entry screen, is popped up by the bootloader. So it happens in like seconds when the machine's powered on. So it's a pretty sweet attack vector. So if you have a look at the LSPCI output there, you can see the expansion ROM, and when I saw that I was like, yes! So good. So we can build an EFI like option ROM image with the EFI ROM utility that's part of the EDK. I'm not sure why I use those PCI device identifier and manufacturer identifier. I think that's what the original option, like Pixie firmware, had, which doesn't match the chipset, but Broadcom actually provided a nice little flasher utility for writing the Pixie firmware down, and that seemed to like those IDs, so that was fine. So we create our option ROM image. We boot into FreeDOS on a Mac, which is hilarious, and use the little Broadcom flasher utility to. So we have to have this connected at boot time, so it's on the PCI bus when DOS boots up, and then we can flash a driver down to the option ROM on board the Ethernet adapter. Yeah, so that's pretty cool. So I'm going to show you a couple of quick demos. I've gone through everything really quickly because we're running out of time, and I think I'm doing okay. So I'm going to show you a couple of quick demos, although I'll leave the Thunderbolt one till later because I've got to reboot my machine. But so I'll show you a quick demo of just like a basic evil MAID attack using USB, that just without even writing anything down, just a once-off like patching the kernel. So we boot from a USB flash drive, which has on it a malicious bootloader, like a shim bootloader, that basically just loads a driver that's adjacent to it on the flash disk, and then inspects the NVRAM to work out where the system should be booting from, locate that disk, find the bootloader on that disk, and then execute it, right? So in the meantime, the driver is registered for exit boot services callback, and then when it does get called back into it, patches the kernel, kind of as discussed before. So Hopefully this works okay on this guy. Oop, that way. Alright. Pretty secure. So what I'm going to do is attach the, I've already done it, attach the USB flash drive into the VM here. I'm going to demonstrate on VMware so I don't have to reboot my machine again. So I'll reboot the VM. And hold down the Option key to boot into the boot menu here, and that's VMware's EFI firmware, so it looks slightly different to Apple's boot menu. And it hasn't seen my USB drive for some reason, so let's try that again. VMware seems a bit flaky with that. Okay, whatever. Thanks, VMware. It does this thing where it doesn't actually enter the boot menu and just boots from the first device sometimes, so I'm just going to try this one more time. Okay, so we boot from the USB flash drive, which you saw very quickly there flash up something that looked like exploit output, which was just the driver getting its exit boot services callback and then patching the kernel. So now the kernel's continuing to boot. I've got it in verbose mode because I always do. And once we have the VM actually start up, got our little rootkit command line thing here, and we call the hooked syscall and hopefully get a root shell. So yeah. So let's basically just use the technique that we talked about before with like sticking a payload into page alignment padding that jumps off to another payload in the EFI variable and patches the kernel and all that stuff. So yeah. Sweet, I'm glad that worked. Patching kernels in demos. Yeah. Okay, so I'm going to do another demo, but I'll do it at the end just because I have to reboot my machine. So I'm going to demonstrate the same thing using a Thunderbolt adapter. And it's going to be a weird demo because you won't see some of it happen because it happens on my screen, not on the projector, but whatever. So in case my demo didn't work, there's a screenshot of my boot screen. So I finally got my pre-boot graphics working, and my friend who's an artist drew that for me because he's a legend. So that's my rootkit's called the file. And then there's the kernel patch screen that you saw flash up really quickly. So a few defensive measures, because I guess we have to talk about defensive measures. So EFI firmware password doesn't do a whole lot. Basically, for those who don't know, you set an EFI firmware password and it stops you from changing the boot target, right? So you can't, if you hold down the Option key to go into the boot menu, you can't do that. You can't boot from the network or whatever. So you enter the firmware password. So it does prevent those kind of USB or network or firewire or whatever base level MAID attacks, but it doesn't prevent loading drivers over Thunderbolt because they just get loaded. Anything connected to the PCI bus gets enumerated and option ROMs loaded from regardless of the firmware password, so it doesn't change anything. There are also a few ways to remove them on various machines, like you can reset the NVRAM entirely with like some weird tricks where you remove like one of the RAM sticks and hold, stand on your head and hold down Command Option PR or whatever. I guess that's kind of hard with current Macs because it's all soldered on, so I don't know if that's really a defensive measure or not. But yeah, like it set one, but it doesn't really protect you from that much. UEFI secure boot is pretty cool, I guess. I'm not going to go too deeply into it, but it's basically just driver signing for EFI. So there's a set of keys stored in NVRAM that are used to verify the vendor signatures on the drivers at boot time. So the DXE phase, when it loads a driver from an option ROM or from whatever, checks the signature and doesn't load it if it's not, you know, signed by Apple or whoever. And then the BDS phase does the same thing when it loads bootloaders, so it won't load an unsigned bootloader. Obviously, this has been a big, kerfuffle about this with Linux and Microsoft and requiring secure boot for Windows 8, whatever stuff. So, yeah, it's all interesting. So there's a few issues with that, I guess. So the spec states the public key must be stored in a non-volatile storage, which is tamper and delete resistant, and that doesn't really describe the current NVRAM situation. As I kind of was alluding to with the RAM reset tricks and shit. So if we can flash the NVRAM back to empty, well then, you know, we can probably the system is back to set what, you know, UEFI calls setup mode, so we can boot anything. So that's secure boot disabled. Also, signing really needs to be enforced through the whole stack, because if we can load kernel drivers, then, you know, we can probably mess with stuff pretty severely still, and you know, flash firmware and flash option ROMs, and potentially do other things, especially if there's keys, you know, stored in the kernel for adding new images to whitelist and whatever else. We can just add our own images to the whitelist. But I believe, you know, most vendors will probably just send out new signed updates. So yeah, that's the bulk of it, I guess. There's a few measures, some measures you can take, I guess, against these kinds of attacks, like use an EFI password, because it's, you know, kind of stops some things. Yeah, I guess glue all your ports shut. It's probably worthwhile. I think Apple should implement secure boot, and I think they're best placed to do it of any vendor, because, you know, they have a, you know, homogeneous environment where they know about all the hardware and they know about all the software, you know, effectively. You know, apart from those weirdos that run Linux on their Macs bare metal, or Windows, even worse. So yeah, I guess the other thing that they could do is disable loading option ROMs or drivers from option ROMs off bus expansions, so like off Express Card and Thunderbolt devices, and anything outside the case, basically, which would be a reasonable stopgap, because implementing secure boot is going to be, you know, pretty difficult, and well, not difficult, but like it's a pretty big undertaking compared to like that sort of thing. I think the EFI code needs a good solid audit, because people have already demonstrated that there are going to be some sweet code execution bugs in there, and it's a big code base, so there's plenty of places for bugs. Yeah, so there's some references for, you know, the EFI specification and all that stuff. Slides will be up online, and you've probably got them on a CD, although they'll be an older version, but they'll be up online if you want to check those out. And yeah, that's pretty much it, I guess. So I'll show you the little Thunderbolt demo quickly. So what I'm going to do, I have to actually disconnect the display, because I'm going to plug the Thunderbolt adapter into the one Thunderbolt port on my MacBook Air. So I'm going to plug this little guy into here. I've got a better demo, like that actually does infect the machine, but I don't really want to mess with my brand new MacBook Air too much, so I'm going to just use the same payload as I just demonstrated. So rebooting my machine, and so it'll load the same driver that I just demonstrated loading off the USB flash drive off this little guy. So maybe, come on, alright, whatever. Oh cool, it panicked my machine, good. I hadn't even rebooted at that point. Okay, yeah, so I'm powering it on, and of course you can see that because there's a big light shining on me, so that's really helpful. So it's going to boot up and load the device driver.
Have you played around with parallels to see if it accidentally did VMware web?
No, I haven't really. I know they all kind of have their own implementations of EFI. Like VMware stuff is pretty heavily modified, and they're really helpful with telling me how to do things on their forums and stuff. But yeah, I haven't looked at Parallels at all. I think VirtualBox has their own implementation as well. There we go. Kernel's patched. All right. Thanks very much, guys. Any other questions?